Hello, I'm Arjun, and I'll be presenting our work on improving vision and language navigation with image-text pairs from the web. This is joint work with Ayush, Stefan, Peter, Devi, and Dhruv. In VLN, an agent is placed in a photorealistic environment, such as the one shown here, and presented with natural language navigation instructions shown at the top that describe a path to a goal location. This video illustrates a path that follows these instructions by entering the hallway and eventually ending up in the bedroom containing the round mirror and butterfly sculpture. As you might have noticed, identifying the visual landmarks mentioned in the instructions, such as the butterfly sculpture, is critical to solving this task. However, a key challenge is the long tail of such concepts that we might want our agents to recognize. For example, here's a histogram of nouns in the VLN training data. We see a long tail in this dataset, with common words on the left and the words to the right occurring only once. In prior work, VLN agents typically learn visual grounding primarily from this dataset. So if you want these agents to find the marshmallows, you're probably out of luck. How do we learn visual grounding for these types of rare concepts? Recently, there's been substantial progress in the vision and language communities on the problem of visual grounding in static images. These works utilize transformer-like models and BERT-like pretraining objectives to learn visual grounding from large-scale web data, which is easy to collect. This raises our central research question: how do we transfer visual grounding from large-scale web data to the embodied task of VLN? There are two key challenges with this type of transfer. The first challenge is transferring visual grounding from static images to the sequential data we must process in VLN. The second challenge is that there's a domain shift between the internet data shown on top and the type of data collected by embodied agents on the bottom. Typically, if an internet image caption mentions a couch, the couch will be in full view, whereas in VLN, the viewpoints are determined by the navigation path, so agents must recognize couches at skewed angles. In this work, we propose a model architecture and training curriculum to address both of these challenges. Our model, denoted as VLN-BERT, is composed of the two-stream structure shown here. Both streams are composed of BERT-like architectures and connected with cross-modal attention layers. The inputs to the language stream are word tokens from the navigation instructions. For the vision stream, we run an off-the-shelf object detector and treat the detected regions as visual tokens. The output from our model is a score that measures the compatibility between a path and the navigation instructions, and we use this score to rank paths for a path selection task in VLN. By design, VLN-BERT extends prior work in vision and language, enabling straightforward transfer from vision and language to vision and language navigation. To train our model, we propose a three-stage training curriculum where we progressively train on language data, static image caption pairs, and sequential path instruction pairs. We ablate this training curriculum and find that language-only pre-training improves performance over a no pre-training baseline. We also find that independently, stages 2 and 3 lead to another 5 absolute percentage points of improvement. Finally, when we combine all 3 stages, we see further synergistic effects, with another 9 absolute percentage points of improvement. Additionally, VLN-BERT's ensemble model performance improves substantially over the prior state-of-the-art on the VLN leaderboard. This qualitative example provides a feel for VLN-BERT's improved performance. The navigation instructions describe a path that turns right, then left, then right, and eventually ends up near an antelope head. The path selected by VLN-BERT is shown in blue and ends at the same goal location as the ground truth path shown in orange. Thus, there's no navigation error. We use a gradient-based technique to inspect which regions VLN-BERT uses to select this path, and the top 5 regions are shown here. In this case, we see that VLN-BERT was able to correctly ground the phrase antelope head. This is neat because the word antelope occurs only 3 times in the VLN training data, but 138 times in conceptual captions. Thus, it's likely that the visual grounding was learned from there. Thank you.